Okay, this video is a supplement, full solutions video for exercise 3 and 4 of lesson 8.4 intersections of lines in 2 space and 3 space. Okay, so I'm actually going to solve these questions using a mix of geometric and algebraic approach. I'm going to use my geometric understanding to find shortcuts for myself and help me understand the situation. And from there, I'll use the algebra to support my arguments. Okay, determine if these lines intersect. If they do, find the coordinates of the point of intersection. So you see that the lines are in 3 space, x, y, z. So it could be one of, 4 different situations, but let's analyze. My geometric analysis first takes me directly to the direction vectors. And what do you know? The direction vector for the first line is equal, not even scalar multiple, but equal to the second line. That tells me that line 1 is either going to be parallel to line 2, or line 1 will actually be the same as line 2. There's no other option, right? Line 1, they're going to be parallel because they have the same direction vector, or they are the same line if they have the same direction vector. There's no other possibility. Okay? So what would I do as a shortcut? I'm going to try to verify a point. Like, for example, I know the point 5, 11, 2 has to be on line 1, and I know the point 1, negative 9, 9 has to be on line 2. If they are the same line, then I should be able to find 1, negative 9, 9 inside line 1, and vice versa. So how about this? I'm going to take line 2. In line 2, my x must be 1 plus a t. My y must be negative 9 plus 5t. And in z, it must be 9 minus 2t. So if they are the same as line 1, I should be able to find 5 as x, 11 as y, and 2 as z. So let's do it. If 5 equals 1 plus t, t must be 4. Okay. Well, do I get 11 when I plug in t as 4? Negative 9 plus 5 times 4, that's 20. Nice, I get 11. Let's try it here. If I plug in my t, I get 9 minus 2 times 4, that's an 8. And I get a 1. Uh-oh, I'm supposed to get a 2. So when x is a 5, y is 11, but z is a 1, not a 2. In other words, the point that is found in L2 is not found in L1. The point that is found in L1 is not found in L2. They may have parallel or collinear direction vectors, but they are not the same line. So I would say, since 5, 11, 2 is not found in line 2, the lines 1 and 2 are parallel but distinct. And that's it. That would be you trying to verify a point. Instead of just simply verifying a point because I went about it in a geometric way, you can still provide a very strong argument by looking for a specific point of intersection. Right? Let's say you didn't notice that and you're like, I know that in line 1, my x value has to be 5 plus s, and in line 2, my x value has to be 1 plus t. Okay? And I'm going to get myself an equation. If they do intersect, then at some point, the x of line 1 and the x of line 2 should equal to each other. So I've got an equation there. My y, it should be 11 plus 5s, but at some point, the y should be also equal to negative 9 plus 5t. My z should equal to 2 minus 2s, but at the same time, it should equal to 9 minus 2t. Excuse me. So I've got 5 plus s equals 1 plus t. I'm going to, just because s and t are isolated, how about I substitute today? Subtract 5 from both sides, I get t minus a 4. So anytime I see s, I'm going to plug in t minus 4. Take a look at my y. 11 plus 5s equals negative 9 plus 5t. But I just found s is not just s. I'm going to rewrite s as t minus 4. So we've got 11 plus 5t minus 20 equals negative 9 plus 5t. Let me rearrange. Ooh, interesting. Plus 5 plus 5. If I subtract both sides, I actually get 0t. And then that's a negative 9. Add 9 to both sides, I get a 0. Interesting. I get 0 equals 0. What does that mean? Well, let's keep going. Let's pretend we don't know what it means. Keep going. If I plug in for z, 2 minus 2s is the same as 9 minus 2t. You work it out, and you will end up getting 1 equals 0t. In other words, 1 equals 0. Okay. What does that mean? S and t have a relationship, but for y, it could be any, and they will essentially intersect. But the z, it's impossible. There is no intersection for z. So it's a bit wonky. There's a lot of question marks to it. All you really have to do is look at this part and say, I don't care what x and y has to say, but there is no way the z's can equal because one cannot equal a 0. Okay, so therefore it is parallel but distinct. Okay, so let's move on. Exercise 4. Determine the number of solutions for the following linear systems. Okay, I have 2. Let's see if I can separate this question in half and try to organize my thoughts in a nice, clean manner for your benefit. Step 1, I'm going to check to see the direction vectors. It's so easy. It's so nice for me to try to classify the scenarios from our handout right here. Try to figure out which situation am I at and then dig deeper. So I'm going to look at the direction vectors right off the bat. I don't even have to analyze. I see that M1 is not parallel to M2. So that means line 1 is not parallel to line 2. So what are my options? Could it be that they are exactly the same? Of course not. Could they be parallel? Of course not. It's either they have one point of intersection or they have 0 point of intersection. Let's do it. Let me draw a scenario. So it's going to be either a line or a vector and a vector. So the line 1 and line 2 is going to intersect at a point, or I have a line and this vector is way underneath, and there is actually a distance between them. Okay, it's one of these two. So let's investigate. Does x ever equal the same number on line 1 and line 2? And if it does the parameters of s and t also make the y's equal and the z's equal? So line 1, my x equals 7 plus 2s, and my x for line 2, x equals 3 plus t. And so I'm gonna do it in one shot. 3 plus t. There's one equation. For my y for line 1 is 2 plus s, but from line 2, it's got to be 9 plus 5t. So there's my second equation. For z, for the sake of poor form, how about I do that? Okay, 7 plus 2s, and we've got 2 plus s. And for z, we've got negative 6 minus 3s is equal to 13 plus 5t. Let's do it. I am going to, how about this time around, I won't do substitution, let's do elimination. I am bringing the variables to one side, so my first equation is 2s minus t equals negative 4. My second equation is going to be s minus 5t equals 7. Okay. I will multiply one of them by 2. So that becomes 2s minus 10t equals 14. And since the s's are the same, I will subtract top to bottom. 2 minus 2, that's a 0. Negative 1 minus a negative 10, that's a positive 9. And negative 4 minus 14 equals negative 8. T equals negative 2. If that's the case, let's figure out what s is. S must be s plus 10 equals 7. S is a negative 3. Okay. Since s is negative 3 and t is negative 2 when the x's are equal to each other, will the y's be equal to each other with the same parameters? Well, let's check. 2 plus s equals negative 1. 9 plus 5 times t equals negative 1. Check. Z. Negative 6 minus 3 times s equals 9 plus 3. 13 plus 5 times t, 3. Checks out. Woohoo! That means, because all 3 work, there is only one solution, and it would be x is, oh, I actually didn't calculate that, did I? So let's calculate it. X is 7 plus 2s, that is 1, and 3 plus t, 1. 1, negative 1, 3 is my point of intersection. Okay, that's it. So I'm going to do the exact same analysis for question B. I'm going to look at the direction vectors. And right off the bat, I see that they are not parallel. So it's going to be the same situation. Either they're going to have a point of intersection or they're going to be spaced out. So let's try it. Line 1, my x is equal to 5 plus s. But from line 2, if there is a point of intersection, there should also be equal to 2 plus 2t. My y, I keep doing this. My y would be negative 4 plus 2s, but that could also be 0 minus t. My z, negative 2 plus 3s, 1 minus t. You know what? Just because I have this, maybe it's easier to substitute this time. So I'm going to say t must be, positive t must be a positive 4 minus 2s. Let's plug that in everywhere. If x is 2 plus, for the x's, 5 plus s is equal to 2 plus 2t, which is 2 plus 8 minus 4s. Bring all the s's to one side. 5s equals 10 minus 5. That's a 5. S equals 1. If that's the case, t equals 4 minus 2 times 1. T must be 2. Okay. I'm almost done. So I have my s. If the x's are equal, s must be 1 and t must be 2. Do the y's equal? Well, y is equal to negative 4 plus 2s. That is a negative 2. On the right side, y is equal to negative t. Oh, they both check out. Looking pretty good. Z, negative 2 plus 3s. That's negative 2 plus 3, 1. And t for z, 1 minus t. Ooh, does not check out. What does that mean? It means they don't have a point of intersection. They are skewed lines. Okay. The s and st that makes the x value equal does make the y value equal, but does not make the z value equal. And so there is no point of intersection. So I will say there is zero solution. The lines are skew. And there it is. That brings us to the end of the video. I hope it helped. Exercise 5, as I said before, we are going to leave for Monday. If you are not going to be here for whatever reason, I highly recommend you ask friends, you come see me, do whatever you need to. Be resourceful, use a textbook. It all explains the stuff to you. Okay? Best of luck, and I'll see you when I see you.